So a while ago I did a video series on writing an Altair emulator, and I did mention in that series that I would be releasing the source code for what I'd done. And I've sort of procrastinated with that a bit, but now I'm ready to put that source code onto GitHub for everyone to fiddle with. Now, it's not what I would consider good code. It's very messy. I've not really had the time to get it into any sort of presentable state, comment it properly, document it properly. So it's just supplied as is. You can do with it as you will. There have been a few changes since the last update on this topic. I have ported the CPU emulation from C# to C++, and I've done that simply because of speed. I wanted to run the CPU tests to make sure that everything was working properly, and the C# emulator just wasn't capable of going fast enough to be able to do those tests in any reasonable time. I mean, one of the tests, if you run it on original hardware, it takes hours. So I needed to get the speed of the system up as fast as I could, and the only real way of doing that would be to rewrite the CPU emulator in C++. So here's the solution, and you can see here there's the 8080 emulator code in C++. Now this isn't one I've downloaded. I have actually written this, and if you look through the actual C++ code, you'll see that it is very, very similar to the C# code. It's just been basically ported. Let's show you how different this thing is now to what it was. So let's run the software. So you can see I've got all of the status LEDs now. I've got the address and data LEDs. I did have those before, but they're a little bit better now. They don't just blink, they actually dim like the real hardware does. The sense switches are there, and you've also got similar situation to the front panel switches on the Altair. I've just had to change them a little bit because coding a custom control with 3 positions was a little bit problematic, so I had to take a bit of license there. You do have run and stop, reset. Reset will reset the system, basically set the program counter to 0, clear all the registers, and then start running from 0 again, if you were in running state already. I mean, if you're in stop state, it would just basically clear all the registers. That's when you left click it. When you right click it, it does a hard reset. Now that's the same as a reset. It clears all the registers, but a hard reset will also clear all RAM as well. And if you're in running state and you do a hard reset, it will stop. Step is just the same. It will just step through instructions. Again, examine and deposit will basically do the same thing as the Altair's front panel. But what I've done is I've changed the toggle switches. The way you used to do it on an Altair was to set all the switches. I've replaced these with text inputs, so it's kind of easier to do. So if I go back to address 0 here, so if I want to deposit octal 10 in there, I can deposit it. And then I want to put 111 in the next, and maybe 254 in the next. Yeah. So it works pretty much the same. It's just that it's a lot easier to do with the text input there. And you can switch this from octal to hex if you like. Now over here, this is a bit of a mess. I really need to tidy this up, but it's still functional. You've got a display of all the registers, all the flags, and if you want, you can flip to monitor mode here, which will show you a memory area. And in here, you can basically trace out. So you can see, if I were to step through here, you can see the program counter increasing. So you can go to where BC is pointing to, where DE is pointing to, and so on. And wherever those registers are pointing to, it will show in that color in this readout. You've also got a disassembly readout there for the current address. Commit changes, just if you can basically change a value here. So you can see those are the values I put in. I can change that to say FF, basically send them back to the Altair. If I start this, let's do a hard reset. I'm just going to be running NOPs basically throughout the entire memory because all of memory is 0. If I turn status off, it will stop updating the status. Turn it on and it will start updating it again. The reason that's there, obviously doing all this, updating all the LEDs and calculating what brightness there needs to be, takes time. So if you want to be running the system flat out, what you would do is turn status off like that and set the speed to 1. A speed of 1 is a special speed to the CPU emulator which tells it to not do anything other than emulate the CPU. So it doesn't bother with calculating the status LEDs, and it doesn't bother with sending that data back to the C# side. So that's basically what you want to do if you want to run something absolutely flat out. So let's just put this back to 500. Yeah, it does say there with speed 1 that the system speed will be 1 gigahertz. That's not really true, that's theoretical. The actual maximum speed is going to be dependent on how fast your system is. On mine I get roughly 100 megahertz when it's running flat out, somewhere around there. I haven't calculated it properly, but somewhere in that region. Right click for a hard reset, that's always a good idea. And we're going to load a hex file. I've got a bunch of stuff here, but I'm going to load Kilobit. So when you load a hex file, it will put the start address of the hex file, or the lowest start address of multiple hex files, into this address. Yeah, so all you need to do is click examine, and that will send you to wherever that hex file was loaded. Now of course kilobits runs from 0, so it was at 0 anyway, but if you're loading something like the disk bootloader, you will need to do that. Okay, so we're now at address 0, we've got kilobit running, we've got all the sense switches turned off, we hit run, and you can see kilobit is running. Now specifically for kilobit I put this option in, sense switch moment reaction. So when that is ticked, when you click a sense switch, it will only click once, it won't stay toggled. And I did that just for playing Kilobit because it was too cumbersome to turn it on and off like on the real hardware. Oop, missed that one. Got it. So we'll go through the same sort of stuff as we did before. So we can load a hex file. So if I'm going to load, let's say basic. Oops, I forgot to set the dip switches. Okay, load hex file, cassette, examine, and run. Send to device cassette, and I'm going to send extended basic in there. And there we go. And we're in. On the terminal screen here, we've got a bunch of options. So what Control C is, if you have Control C enabled and you press Control C while that is enabled, it will generate an interrupt on RST0. Okay, that's all that does. And that's useful in CPM or something if the program's locked. I mean, you can just hit reset, but if you're using the terminal window, if you're using an external program like PuTTY, that can be actually useful. Bell and flash. ASCII character 7 is terminal bell. So you can see if I run that, we get a flashing screen and a sound. Now if I turn bell off, we just get a flashing screen. If I turn flash off, I can log into this through Telnet. All that does is it turns that feature on and off. That's all. CLS, ASCII character 12 is form feed, and that translates with terminals to clear screen. So if I run this, you can see it clears the screen. If I turn CLS off, it doesn't clear the screen. Okay, backspace equals underscore. So you might be aware with earlier versions of BASIC you couldn't do a backspace. So if I went prompt, okay, and I wanted to backspace, I can't do it. What I would have to do there is go 3 characters, so underscore, 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 int. If you turn BS equals underscore on, it will do all this for you. You can actually press backspace. So if I do that again, you can see I can actually use backspace normally. That's what that's for. It's only really meant for BASIC. Echo. Okay, let's just reset the system. Now normally if there's nothing talking to the terminal device, right, you're not going to get any echo back. If you turn LF on, when you press return, instead of just sending a carriage return to the system, it will send a carriage return and a line feed. Some systems require that. And clear will just clear the screen manually. So I've demonstrated CPM before, but let's drop it in. So I'm going to put CPM in that disk, and then I'm going to load the disk bootloader. And this time I do have to hit examine to get it to the correct program counter. Hit run, and we're into CPM. You can see standard stuff there. Now what I'm going to do is perform a CPU test. Because CPU tests take a long time to execute, I'm going to switch this into full speed. So I'm just going to stop execution, switch speed to 1, and turn status updates off. Now it will be running flat out. So click run again. Now I'm going to run CPU test, which is one of the tests. Now this test normally takes about 2 minutes-ish. You can see that completed quite quickly. Now I'm going to run 8080 EXM, and this test on real hardware, as far as I'm aware, takes hours, and even on this system it still takes a while. So I'm just going to leave this running, and I'm going to do a jump cut to when it finishes. Okay, it should start to complete pretty soon now. This one is the longest one. There we go, passed all the tests, which is good. Let's just put this back to normal speed. Now on here, on center device, you've got cassette terminal and 88SIO. Now 88SIO is actually a modem emulator. You don't really want to be sending to and capturing from that. But what it's used for, let me insert another CPM disk which has Kermit on it. So there's Kermit. Load the disk bootloader, examine, run. Okay, so we're in CPM again. And I'm going to run CAN 411. Now in here you have to tell it what port it needs to talk to. The way it does that is set port UR2. So it's UR2 on this system, that's where the modem is emulated. And I can type connect to talk directly to the emulated modem. You can see I've got OK prompts coming back. So this is just a basic raw implementation, but I can connect to a system. So if I type ATDT, standard Haynes modem commands, but I type in a host name and it will connect to the telnet port. One of those is telehack.com. This is a famous one. I hope it's running. There it is. And there we go. So we can actually get online with this in a way. The telehack telnet system runs some of the commands here. Now on some systems you will have to put this LF on, because it depends how the telnet server is running. On this one it's okay, but on others you might need to just click LF on, so be aware of that. So let's come out of here. So +++, ATH for hang up. What I'm going to do is increase the speed about twice, and in disk 1 I'm going to put some, I've got some CPM games here, so I'm going to put that in disk 1 and examine and run. I'm going to go in with the with putty. I'm going to run a different game this time, so we're going to run I've got a catch up, there we go. This is like Pac-Man clone, one player game. Yeah, that's running. And I'm dead. He's chasing me. Got him. Alright, that's enough of that. Okay, one more thing that I've put in here, which is pretty much pointless, but I wanted to do it. Get this back to normal speed. What I'm going to do is I'm going to load BASIC again. Okay, so if I write a small program here, so let's say I wanted to save that to cassette, actually to cassette, so plug a cassette recorder into the computer. What I can do, I can turn cassette audio on and see we get a tone. So if I type csave, and also if you were to center device when you've got cassette audio on, it will actually listen for those tones and load them back in. So you can physically load and save from an actual cassette player or any audio system really. So that's about it with the updates. So what I'll do in the description. I'll upload all of this, what I have at the moment, to GitHub, and whoever wants to can download it and play about with it. And it should be a self-contained project, pretty much. The only thing it requires is, for this cassette audio, it requires the only thing it requires is the N-audio package. But it should, if you've got an internet connection when you load the project, I think it should download that for you when you first open the project. But I could be wrong with that. But if not, you just have to go into NuGet and install it, and everything should be good. This is in Visual Studio 2022. The only thing that I've disabled, nullable objects, I've disabled that because it was too much work to convert the code. But other than that, it should just load and run straight away. Have fun with it. If you want to play around, let me know any updates that you might make, and obviously I'll continue to tinker with it myself and post updates onto GitHub whenever I add functions. Some of the functions that I want to add is stepping. Let me show you. Let me load the disk bootloader here, click examine. Now if I go into the monitor, you can see here this is what's loaded in, and if I step through this in, you can see here we've got sort of readouts. I'd like to have this not just one line, but showing a lot more instructions, like all the instructions following and previous. Going back in instructions is not actually easy, going forward is. And I want to put things like breakpoints and stuff like that in here. Now stepping on this system actually steps an entire instruction. It doesn't step through the cycles like the real hardware does. Now in earlier versions of this, when I was using the C# CPU emulator, I did actually set it so that it did that, but it was very greasy. It was very messy the way I had to implement that, and I figured if I wanted to do it more neatly, I would have to rewrite the CPU emulator completely to do it cycle based, and it was just basically too much work. And when I rewrote everything into C++, it became even more complicated to be able to do that. But I do have an idea on how this could be done, and it would involve virtually stepping through. When you're in the stepping mode here, you're waiting to execute an instruction. When you click step, instead of actually executing that instruction right away, if there are multiple cycles to that instruction, it will do it virtually on the C# side. And when you're out of that, it will then tell the C++ side of things to execute the instruction. So I think that might be a viable way to do that, to fully emulate the real hardware. But just for now, it's not really that important. You just step through each instruction rather than each cycle. Which means, of course, the only thing you're ever going to see are these three status lights when you're, well, maybe the IE light if they're on. But that's all you're going to see when stepping. But when you're running, it does update these properly. So anyway, that's about it. See you all later. Bye.